All right, Chapter 12, review session. Again, we're going to try to quickly work through some of these again in class, really throughout the entire time while we've been working in Chapter 12. We've been doing problems like these, of course, but specifically the last couple of days, we've been really trying to hammer home some of these points, some of these facts, some of these approaches. So we're going to go ahead and start with problem like number one. And I know that if we're not looking at this the right way, this could be pretty tough. So when we're approaching a problem like this, again, we have to pay very close attention to the entirety of the problem. Again, specifically right here where we're talking about the limit as x approaches -2 from the positive side. Again, the reason why that's so important is that now I know specifically which side to approach from. And what I mean by that is that if that were not there, and meaning if we were, I know that we demonstrated the same way in class today, if we were trying to find the limit as x approaches -2, that limit does not exist. But if we're approaching just from the positive side, that tells us, again, if I'm approaching 2 from the positive side, that I'm coming this way. I'm starting, it looks like, at 3, I'm getting closer, there's 2, I'm at 1, I'm at 0, I'm at -1. I'm getting closer and closer and closer, but I eventually get there, and at that particular value, now we could say that my limit here is going to be +5. Had the circumstances of this problem been different, like I said, had we been, oh wow, that was weird. Had we, try to line that back up, had we been talking about a different limit altogether, like the limit as x approaches -2 from the negative side, well, then we would have been talking about this line here, which would have been vertically, again, we're looking at this, then that would have been at -1. But since we're talking about approaching from, not the negative side, but from the positive side, that's the reason why we're coming at this from the greater than, from the right side, I suppose, and that's why we're saying that it's 5. If we were to go back, just to revisit one more time, if we were not approaching from either side, we're talking about the entire limit. Again, the limit as x approaches -2, just stopping there. That means that from the left side and from the right side, the less than and the greater than side, we actually have to be approaching the exact same value. So since from the left side we're getting -1, and the right side we're getting +5, the reason that did I say -1? I'm sorry, it should be +1. That's the reason that the limit does not exist, because we would actually have to show convergence onto the same point. So a couple more. Obviously, as we look, I think it was number 5 on the homework assignment. I was looking similar to that. Yeah, guys, I don't want you to mess with the substitution or direct substitution, indirect, any of that stuff. We don't have to get there, I suppose, if we know what we're looking for on the graph. So if I'm approaching the limit as x, if I'm looking at the limit as x approaches -3 from the positive side, again, here's where s is -3. From the positive side means I'm coming this way, and we can see -4 is going to be my limit. Had that said approaching from the negative side, well, then I guess we would have been coming this way, and vertically it looks like I'm at -1 would have been our answer. So again, if we're talking about the entire limit from both sides, not a one-sided, but from both sides, that's when the limit would not exist. So again, for this particular problem, since we're coming from the positive side, -4 is the solution there. Yet again, this is now kind of what I've been talking about. So not again. This is the one that I've been talking about. Now, if I'm finding the limit as x approaches 3, and that's it. If I were to find the limit as x approaches 3 from the negative side, that would mean that I'm coming from the negative side right here, and I'm looking at +1 as being my limit. But if I'm looking at the limit as x approaches 3 from the positive side, well, that would mean that I'm approaching here, which puts me at 4 for the limit. But as you can see, we're not just from the less than side or just from the greater than side. We're trying to put this entire limit together. So piecing this together, the limit as x approaches 3, since 1 is not equal to 4, for that reason the limit does not exist. So that's what we have to go with. Again, please understand that there's a difference if I'm coming from the less than side, from the greater than side, or if I'm not coming from either side. Specifically, again, if it does not say, like here in number 3, It does not say that we're coming from specifically the less than or from the greater than side. We're just coming for the entire limit. That shows that we have to have convergence onto that same point, that same value. Okay, so on to a problem like number 4. We want to find the limit as x approaches -4. This is one where we could actually use direct substitution. We can put -4 directly in for x. So in doing exactly that, since we have x cubed plus 8x squared plus 21x plus 16, it's now going to be time for us to, as we said, directly substitute -4 in place. Everywhere we see an x, we put a -4. So in cleaning this up, excuse me, if we're to take a look at -4 cubed, we're going to say that's what, -64. Let's see, -4 squared is going to be 16. 16 times 8, that's going to be now positive 128. Whereas -4 times 21 is -84, and plus 16. So if my next move is to actually add these all together, let's see, what is that going to give us? That's going to be -4 is our final answer. For number 5 here on this same slide, get there. This time, this problem is just bizarre. I'm trying to find the limit as x approaches -4 of 1. So if we were to think about using our direct substitution, I'm going to put a -4 in place for x. There, I did it real fast. Hopefully you saw it. No, just going to be facetious here. There actually is nowhere for me to put -4 in for x because there's no x value. Therefore, 1 remains constant. This is going to be a constant function. So as we're continuing on, we would always want to consider that idea, that pathway, I suppose, of direct substitution. But we'll notice when we get to number 6 that if I try to use direct substitution, I put a 1 in place for x, we are going to get 0 in the denominator. So that's obviously a problem. We have to stay as far away from that as we possibly can. So this is where we're going to have to utilize what we refer to as the divide out technique. So I'm going to rework this problem. I'm going to, again, still try to find the limit as x approaches 1 of x minus 1 over, but I'm going to factor the denominator now. So in factoring the denominator, we're looking for what multiplies 2, that's a -3. So I'm thinking about x minus 2 and x minus 1. And the moment we see that it's written out this way, hopefully we can recognize that, yeah, the x minus 1, so they cancel out, which is going to leave me with still the limit as x approaches 1 of, now we're talking about 1 over x minus 2. So at this point, we have no problem with directly applying the limit. So meaning directly putting 1 in place for x, so 1 over x minus 2, but again, in place of the x, we are going to put a -1. So that leaves us with 1 over -1, which, of course, 1. Same thought process over here with number 7. I cannot use direct substitution. I put a 2 in place for x. I quickly get 0 in the denominator, and that's a problem. So what we are going to want to do in a problem of this nature is what we refer to as the rationalization technique. So if I had the square root of x plus 7 minus 3 over the quantity x minus 2, I'm going to multiply the numerator times its conjugate here. So I'm going to multiply by the conjugate being the square root of x plus 7 plus 3. If we do that on the top, we have to match and do that on the bottom. Plus 3. So technically, in the top, we would be absolutely fine if we decided to FOIL this out. But what you're going to notice is that things might get a little difficult to track. So if we were to go with the same generic example as I always use, a plus b, that's a binomial. If you multiply by its conjugate, a minus b, every single time, it's going to work out to where we multiply the first, the outside, the inside, and the last terms. It's always going to work this way, and it's always going to work to where the middle terms cancel out. So what we can say is shortcut-wise, a squared minus b squared is always, always, always going to be our shortcut. So keeping that in mind, that's great so long as we understand, in this case, that the root x plus 7, that's our a, and 3, that is, kind of got away from me, that 3 is our b value. So if we were to take in our numerator, again, by multiplying that out, multiplying those conjugates, we're going to say that we have a squared minus b squared is going to look something like this. Over, now this is, like I said, it seems like a lazy shortcut. The quantity x minus 2 times quantity x, root x plus 7 plus 3. And I'm not actually going to multiply that out. Okay, the reason for that is that I'm hoping for a cancellation to occur at some point throughout this problem. So what we're going to notice is that square root to square root, they're actually just going to cancel each other out. So we're finding the limit as x approaches 2. Now that's going to give me the numerator, try to save the colors here. The square root of x plus 7 squared is just going to be x plus 7 minus 3 squared, which is going to be 9. Over, again, the quantity x minus 2 times the square root of x plus 7 plus 3. And we are getting closer. So in the numerator, x plus 7 minus 9 is going to clean up to be x minus 2. Over quantity x minus 2 times the square root of x plus 7 plus 3. We're still finding the limit as x approaches 2. And we still can't apply the limit until we recognize that those binomials, I should say, of x minus 2, that they're going to cancel out. So I'm still finding the limit as x approaches 2, but now it's of 1 over the square root of x plus 7 plus 3. And we're getting very close. In fact, we can actually now apply the limit. So 1 over the square root of x plus 7 plus 3. But as we said, we're directly going to apply. And now we're looking at 1 over the square root of 9, excuse me, plus 3, which is 1 over 3 plus 3, which, of course, is 1/6. So hopefully we're recognizing and understanding that, yeah, there were a lot of extra steps that we had to take there, but they were all necessary in being able to use our direct substitution. So next, we're taking a look at a problem like number 8. We want to find the limit as x approaches -2. And as we can see here, we've got this disjoint function to where we have two distinct functions that are kind of playing into this. We know that if x is less than or equal to -2, we're going to use the top function. We also know that if x is if x is greater than -2, we're going to use the bottom function. So what we actually are going to do here is, honestly, we're just not going to overthink this. What we need to do is we need to find the limit as x approaches -2, but as I'm approaching it from the negative side, that means that I'm going to be using this piece here. So we're going to evaluate negative x directly, meaning if I have negative x and we're putting the -2 in place for x, we can quickly determine that that value is going to be -2, which is +2. So in doing the exact same thing with my limit as x approaches -2 from the positive side, well, from the positive side, that means that we're here. So now we're going to try to evaluate 2x plus 6. But again, in place of x, I'm finding my limit as x approaches -2 again, so I put the -2 in place. At which point, this is going to give us -4 plus 6, which, lo and behold, is also 2. So for the reason that, because they match up, I guess is what I'm trying to say, that 2 is equal to 2. So as we're coming at this from the less than and from the greater than side, for that reason, the limit as x approaches -2 is equal to 2. Again, had they been different from one another, had the top been equal to 2 and the bottom been equal to 5, then no problem, but the limit does not exist. So doing the exact same thing here at number 9, we're finding the limit as x approaches 0. So when x is less than 0, we're going to use the function x plus 2. When x is greater than or equal to 0, we're going to use the function x squared plus 2x. So in cleaning this up, finding the limit as x approaches 0 from the negative side, that's going to look something like, again, we're using the top, so x plus 2, and we're putting a 0 in place for x, so we can hopefully pretty clear that we end up getting 2. As I'm finding the limit as x approaches 0 from the positive side, well, that means that x is greater than or equal, so I'm going to be using a little bit more complicated looking, x squared plus 2x, and just like before, we're going to decide to put a 0 in place. And this time we end up getting 0 squared is 0, plus 2 times 0 is 0. We end up getting 0. And now I'm noticing, and so are you, I'm sure, that 2 is not equal to 0. Therefore, my limit does not exist. We didn't get the same values. Limit doesn't exist.